we have another Emanuele and David and Riccardo. So guys, please activate your webcam and your microphone. So this is our final presentation. And let me introduce these three gentlemen from the Politecnico di Milano. So Emanuele Tomassi has a bachelor's degree in aerospace engineering with an ongoing master in space engineering at the Politecnico di Milano, and is a mission analyst for the 6S CubeSat mission in Polyspace since December 2021. Davide Bellicoso is a master student in space engineering at Politecnico di Milano and president of the CubeSat and CubeSat system engineers at the Polyspace Student Space Association. And Riccardo Rambaldi has a bachelor in aerospace engineering, currently in the last year of masters in space engineering, both at Politecnico di Milano, and also an ex-board member of the Space Association, Polyspace, and system engineer for the 6S CubeSat project. And yeah, without further ado, I'll leave the stage to you guys, and please start the sharing of your screen.
Yes, thank you very much, Stefan. Good evening, everybody. Thank you very much for attending our talk. We're a group of master's students in space engineering, and today we're going to present you the work we carried out in the framework of our university module in system engineering and operations at Politecnico di Milano, in which we used Capella software and ARCADIA method to perform the reverse engineering of a very well-known space mission, which is ESA Mars Express mission that has been flown some 20 years ago. So this is about reverse engineering, which means that basically we started from the data available in the literature about the mission and the spacecraft, and we went through a preliminary design of all the subsystems and the mission, the trajectory of this mission, as we will have a glance on this about this later on in the presentation. And finally, the objective of this was to retrieve and derive the requirements for every subsystem and the mission itself. Before starting, I wanted to acknowledge our colleague Paolo Minacapilli for being precursor of the MBSE approach and Capella method at our university, and from his thesis this work is based on and takes a lot from. So we can proceed with the outline of our presentation. We're going to start by giving an introduction to the mission we are going to analyze, about its objectives and architecture. And then we're going to go through the core of our presentation, which is how we use the ARCADIA method and Capella tool to perform our work. Finally, we are going to go through fast about some computations about the preliminary sizing of the components of our spacecraft, and eventually we're going to conclude with some considerations. So moving on to an introduction to the mission, ESA Mars Express mission had the objective to monitor all aspects of the Martian environment. This means that we include in this the subsurface, surface, atmosphere of Mars, and also to take pictures of its moons, which are Phobos and Deimos. And the main goal was to search for evidence of extant or existing life on the planet. From this, we can already derive some scientific objectives directly from the statement that has been retrieved from literature. So we can, for example, list them as we have done in the slide, and they include the global mapping of Mars' surface, the study of the composition and circulation of its atmosphere, the surface morphology, and many others, including the mapping of distribution of water on the crust and the flybys about the Martian moons. And last but not least, the in situ investigation, which means that something had to land on the planet's surface as it happened. And then the near Mars plasma and neutral gas environment study and the study of the interaction between the solar wind and the atmosphere of the planet. And here, summarize the architecture of the mission by ESA. So you can see the spacecraft departs from Earth, and after some time it reaches Mars, but before reaching Mars, it releases a lander, Beagle 2, which you can see in the illustration, which is gonna land on the surface, while the satellite is gonna continue its interplanetary trajectory and finally inject into an orbit around Mars to continue its observation. And so before the preliminary sizing of the subsystems, we can already exploit Capella software to compose some diagrams about the requirements of the mission. These are operation architecture blank diagrams in which you can see some of the requirements we derive for the mission itself, and we divided them in categories according to the space standards, the ECSS, and you can see some of them, including the cost of the mission, which shall not exceed 300 million euros, the launch windows, the main functionality that the mission has to perform, and environmental regulations about the space environment, which the satellite has, of course, to survive. And here are a couple of slides about the scientific instruments and the satellite had on board. It's not really to go in detail about all of them. This is just to have the idea that the mission was complex, and we had several payloads both on the satellite and on the lander. But most importantly, each of these payloads, each of these instruments was there for a reason. That was to fulfill one of the previous objectives that we outlined in the previous slides. So, for example, you could see that the high resolution stereo camera payload was there to perform surface morphology investigation, as well as the Mars payload, while the SPICAM was there to study the composition of the atmosphere and the interaction of the atmosphere with the solar wind. And finally, the analyzer of space plasma and energetic atoms was used to characterize the plasma and neutral gas environment. Again, some other instruments. On the right, you can see also those of the lander, which was Beagle 2, and the objectives that are related to it and the rationale. So again, using Capella software, we can retrieve a diagram with that summarizes the requirements for all our payloads. The image is a bit tiny. You are not supposed to be able to read all of them. Maybe I can point out some of them, such as that the system shall be able to perform in situ measurements of the soil oxidizing capability, and that the system shall perform in-orbit measurements for at least a Martian year, and all these kind of requirements that have been derived from studying the data present in the literature. And so, before outlining the approach we used in regards with model-based system engineering, I wanted to mention that basically we did this work to the final goal of this work, after we derived the requirement for every subsystem, was to justify the design choices that the system engineers and specialists that dealt with the mission 20 years ago did while designing the platform. So going on with the approach we used, we exploited only some Capella features. As you can see in the slide, these are the 4 steps in modeling a system with Capella. So going from the operational analysis, in which you you capture the needs from the stakeholders, to the system analysis, in which you identify the system, to the logical architecture and physical architecture. Actually, our task, our work only needed the first two, so the operational analysis and the system analysis. So in the following, we're going to detail more the diagrams that we found useful in Capella, and how we use them to model our complex system. Okay, so let's start from the operational analysis, which, as from Capella definition on the first page of the software, it aims at capturing and consolidating the operational needs from stakeholders, to define what the users of the system have to accomplish, and to identify entities, actors, roles, activities, and concepts. Okay, so the first thing we do is to create an operational entity breakdown diagram to list all the actors and entities, so human and non-human stakeholders, and specify in case if they are included in themselves. So we have ESA, the European Space Agency, the main partner of the mission, the launcher, which you use to launch the satellite, the ITU, which is an entity that basically allocate the bandwidth for a very precise bandwidth, very precise range of frequencies to perform your communications between Earth and the spacecraft. And then all the scientific community and space industries, environment, and mission operations center. Second diagram we used is the operational capabilities diagram, which you use to define the capabilities of your system and specify the relationship with the actors and entities which you defined in the previous slides. So some capabilities we spotted are, for example, to deliver the payload to Earth orbit, and this is done, of course, by the launcher, the rocket on board of which you mount your satellite. To perform space operations, which is done by the Mission Operations Center. To perform the scientific mission, which is done by ESA, and many others, such as assigning the communication frequencies, done by the ETO, and to develop and test the payload by agencies and institutions and industries, of course. So at this point, we have to define all the scenarios in which our mission is gonna operate in. So to do so, we use the operational entity scenarios in Capella, the OES diagrams. We define a bunch of these. For example, in the first one, you can see the workflow that goes from collecting the data to analyzing it, and all the actors that are involved in this. The same for each of the capabilities we saw in the previous slide. So about assigning the communication bandwidth, you have the ITU that establishes the availability of frequencies and gives a precise range to the partners of the mission to be used during communication. And again, some more scenarios that you have to define in order to model the system. For example, on the right, you can see the workflow that goes from the design of the payload to the integration on the satellite and the development of the whole space segment, which is the platform, the satellite itself. And again, a lot of more scenarios, including that relating the operations of the mission operations center, which is responsible for generating the commands to be sent to the spacecraft and to command the spacecraft to achieve its objectives. And so the last step of our operational analysis consists in detailing some operation architecture diagrams, which are useful to highlight some functional chains, such as you can see in the slide, the in-orbit mission life cycle, which follows the blue set of arrows and goes from the design of the payload all along through the launch of it to reaching Mars orbit and to perform operations around Mars. Instead, on the left, you can see the functional chain which regulates telecommunications, which says basically that you have first to generate a command, then to send it to the spacecraft, so you can have the spacecraft actually doing it. And in the second slide inside, you can see the in situ mission life cycle, which is that is undergone by the lander that lands on the Mars surface, and so it lives there and performs another scientific mission, which is different from that of the spacecraft. And now I leave the word to my colleague Emanuele.
Hi all, nice to be here at Capella Days, and I'm going to continue the Davide's words about the operational analysis, talking about the system analysis and what we had to achieve at the end of the system analysis in order to proceed with all the reverse engineering of the subsystems that were part of the Mars Express mission. So the goal of the system analysis is to identify the boundary of the system and to consolidate requirements. The end goal that we had for the system analysis was to produce the data flow diagram in which all the functions of the missions were listed, so that we could use them as a justification for all the design choices that were made for the subsystem that we later identified during our reverse engineering process. So the first thing we did was to identify the system actors and the capabilities of the mission. All the entities that Davide previously mentioned, such as ESA, space industries, the launcher, the scientific institutions, and going on, are now become actors, so that we could link the capabilities and the main missions that we identified could be linked to them. So here in this slide, in the right side, we can see that we found 3 main missions from the literature and the data that we had available, which are the provide support, keep the space segment safe, and to perform the scientific mission. So these were the main missions, and they can be further described by all the capabilities that are linked to them. I can go into much details later on in this presentation, but just to note that all these missions and capabilities can be linked to the actors, such as the Mission Operations Center, the environment, and particularly ESA, that are here shown in the diagram. The single capabilities that were listed before can now be further described by the functions that relate to the system and that the system had to accomplish in order to complete the mission. So each of the capabilities can be described by a number of functions. For example, the approach Mars capability can be described by the functions that are estimate the relative state to the planet, between the satellite and the planet, and to execute the relative maneuvers to reach the planet and insert into the nominal orbit for the scientific operations, as well as, for example, collect data. How do you collect data? You have to check the instrument's status, see that everything works. You have to calibrate the instruments, and then finally you have to operate the instruments. Then all this process is linked to, for example, the provide onboard data handling function here in the left bottom side, where you had to process data, store data, and prepare data for transmissions. So I will not go into detail about every capability, but just to show you a couple of them. We have the provide propulsion, provide protection against mechanical loads, provide power supply. All these three capabilities can be described by functionalities such as generate power, store energy, regulate power, or distribute lastly power. This is the last set of capabilities. And then after all this process that we have done by analyzing all the literature that we had available about the Mars Express mission, we listed all the functions in the diagram called the root system function. Here you can see that we have the three main missions in yellow, which are the provide support, perform scientific mission, and keep space segment safe. And in green, we have the functions of the system that were previously listed. Now I can show you just a couple of slides to see how they are created. So we have the provide support that is further described by provide power supply, propulsion, communication, data handling, and so on, the perform scientific mission, and lastly, the keep space segment safe. So this is the end product of the reverse engineering done into Capella. Now, in order to have a description of the mission and reverse project of the mission, we have to go into much details in every subsystem that the Mars Express had. So what I will tell you now is the mission analysis subsystem, which for the space missions is one of the most particular, because it implies the orbit optimization, the trajectory optimization. So it is different from every other, let's say, project that you can normally perform here on Earth. So for the mission analysis reverse engineering, we divided the process into three main steps: the near Earth phase, the deep space phase, and the near Mars phase. And each of these phases had a similar reverse engineering process. For the near Earth, we always start from the literature to find data such as departure date, launch site, launch user manual. We then proceed with our calculations about retrieving, for example, the initial parking orbit, the escape maneuver that the Mars Express had to perform. And we arrived at the final step of this phase with the data that we can then compare to the data found from literature, such as the orbit parameters and the maneuvers that were executed. Same procedure for deep space. So you find the time between the departure and the arrival on Mars. You find the number of TCMs, which are trajectory correction maneuvers, that were executed in the interplanetary phase. And Then you compute these maneuvers in order to arrive at a precise time and a precise attitude and position with respect to Mars. And you have as final product the maneuvers that Mars Express had to accomplish. Same for the near Mars. You start from arrival date and the type of maneuvers to insert into the final operational orbit, and you compute all the maneuvers for the inclination change of the orbit, from the shape change of the orbit, and you have at the final step the maneuvers executed and the final orbit that the Mars Express had to accomplish. Finally, after this process, we compared the data that we found in the previous slides with the end product and the data that ESA shared for the mission. And we then checked that every data that we arrived had a small relative error with respect to the real data executed. So we proceeded with the justification of all the design choices and with the effects that this particular subsystem had to all the other subsystems in order to continue with the reverse engineering process and the design, going on with the design process. Here you can see a part of the root system function diagrams in which we highlighted the functions that we previously identified that mainly had an effect on the mission analysis subsystem that we just analyzed, which are, for example, here in red, we have the perform orbital control, approach Mars, execute relative maneuvers, and the perform collision avoidance maneuvers. Okay, so the following step was to use also the requirements that Davide described to you before, and so identify which of these requirements had an effect on mission analysis. And just as I just said, in red, with a red square around, you can see the requirements that influence the design choices, such as the compliance with the launcher specifications, such as the mission duration, such as the ability of the mission to land, perform Martian surface operations, and going on. Same process for the mission objectives. So why we decided to have a polar orbit or an orbit with an high eccentricity or with an icy major axis? Because the Mars Express had to accomplish planet observation, communication with the ground station on Earth. So you needed an high eccentricity to be at an altitude high enough from Mars to be able to see the Earth and communicate with the Earth. And why did we need a lander? Because we had to perform in situ investigations, and so we had to optimize the trajectory of the mission to be able to let the Mars Express, and in particular the lander, be able to land on Mars. Lastly, we can retrieve a series of requirements that the mission analysis subsystems had to, let's say, impose on the other subsystems. I can list some of these to you, such as the system had to land with no damages to the Mars surface. The orbit had to remain the same for at least 1 Martian years, and going on. It is not necessary to list all of the requirements, because some of them are very technical and are not useful to explain why Capella was really useful to us. So now I can just let Riccardo talk about all the other subsystems and bring to you some conclusions about our reverse engineering process and why Capella was really useful to us.
Hi, hello everybody. Thank you so much, Emanuele. So the reverse engineering process, which Emanuele just explained, was then employed for all the other subsystems of the Mars Express. And I will go briefly through every one of them. Starting from the EPS, the electric power subsystem, the power consumption of all the components of the spacecraft was evaluated, considering a nominal condition and a worst-case condition. This led to a requirement on the amount of power that the EPS shall ensure in all the different phases. Then we could compute the battery's capacity and the area of the solar panels. After that, we retrieved some design effects which have an impact on the design of the other subsystems. For example, the thermal control subsystem, the TCS, shall dissipate all the heat created by the electric power. And here in the next slide, we can see all the requirements which guided us through the sizing of this subsystem. One important driver of this design, and mainly for the design of the architecture of the EPS, was the fact that the spacecraft needed to receive power both in the sunlight and eclipse phase. So we needed to include batteries in the EPS architecture. So for the attitude control system, we analyzed the needed accuracy in all the phases and the loads on the structure during the control maneuvers. So we could select the architecture and compute the mass and power budget of the subsystem. I'm talking about mass budget in this case because the ADCS architecture included thrusters, which consume propellant mass. This last thing is actually an important design effect on the propulsion system, which shall include this amount of propellant mass in the mass budget computed in the propulsion subsystem sizing. And one of the main driver for this sizing was the needed degree of freedoms during each phase of the missions. For the propulsion subsystem, we used the delta V's retrieved from the mission analysis, and we computed the amount of propellant mass needed, and we could size the tanks. Moreover, we were able to compute the pressurant mass, which is used to pressurize the propellant tanks, and its tank. In this case, we found some design effects, and one important for the structure and configuration subsystem was the fact that the propellant tanks needed structure as support. In this case, an important driver for this sizing, as I mentioned before, was the fact that the propulsion subsystem shall be capable of doing attitude control maneuvers. So thrusters shall be included in the propulsion subsystem architecture. Then we analyzed the amount of data to transmit for the telecommunication subsystem. And so we were able to select the system's capacity and justify the chosen antennas. In this case, one important design effect on the attitude control subsystem was the fact that there is the high gain antenna needed a fine attitude in order to work well. And an important driver for this sizing was, for example, the band that was needed in order to communicate from the orbiter to the lander. So after that, we almost finished with these overviews of the subsystem. We have the thermal control subsystem. In this case, we have considered the worst case scenarios, both for the minimum and maximum temperature. And then we could propose a possible architecture and some possible coatings for the exteriors, in addition to justify the real ones. In this case, an important effect on the EPS was the amount of power needed for the thermal control subsystem in order to work. And an important requirement that is always important when you have cameras and sensors on board in your spacecraft, you have to design the thermal control subsystem by evaluating the range of temperatures in which all the sensors, all the cameras should work. So this was a really main driver for this sizing. Then, having sized all the subsystem, we reconstructed the final design through a 3D drawing software, as seen in this slide. And we had to consider some requirements for the configuration. For example, it was necessary to avoid the shadow on the solar panels from, for example, the antennas. So we started from the right side of the V diagram, and then we were able, through a reverse engineering process, to design all the subsystem, considering the requirements effect between them. And we were able to justify all the design choices of the actual mission. Justifying all these choices helped us to understand the complex practices behind the space mission design. We could see the mutual effects between the subsystems and how it was possible to trace each decision taken to a precise requirement, underlining the importance of listing and writing all these requirements. The Capella model-based system engineering tool helped us to keep track and visualize all the requirements more easily, in addition to understanding and underlining the correlation between the subsystem and the entities through the operational and functional diagrams. So I need to say that at the beginning, it was a steep path of learning, but after that, we were able to use a software which gave us all the tools needed to support the system engineering work for space mission design. Thank you so much for your attention. I leave our contacts on the slide if needed, and if you have any questions, we will answer to them.
Thank you, guys. Thank you for this presentation. I don't see any question in the Q&A yet. So if any of the attendees has some questions for you guys, don't hesitate to put it in the Q&A. I've got one question, which is, you said you were able to understand and justify the choices that were made in this mission. I'm curious if you were able to find some choices that were not that easy to justify, and if you find some, way of doing things differently, optimizing them, maybe, I don't know.
Well, this is a very common question, I can say. And the answer is yes. We find, in particular, one very big choice regarding the trajectory of the mission. That implied the fact that the original trajectory had to aim directly at Mars in order to let the lander, let's say, land on the Mars surface. And before crashing onto Mars, the lander had a parachute that was deployed for the landing process, and the orbiter had to perform some maneuvers before crashing in order to inject onto the Mars operational orbit. But during this procedure, the lander never communicated with the orbiter, and so it is. So we can presume that the lander crashed into the Mars surface, as we never received information about it. So maybe we thought that aiming directly at Mars was a great choice for the optimization of the trajectories and the propellant used. But maybe there were some, let's say, procedures that were not considered for a safe injection into Mars. So maybe aiming for a different point or for a different point in space, and then after the orbiter was safe around the orbit, release the lander and let it land on Mars surface with a parachute in safety, and not just throwing it into the surface. So this was the main choice that left us surprised.
Okay, thanks. Great feedback. Okay, so we've got a bunch of questions now. So very interesting work, guys. Did you document it in a paper from Phyllis? Hi, Phyllis.
Yes, actually, we wrote a report on it. We're gonna share it soon on our LinkedIn pages. So if you want to have a look at it, you can just follow us on LinkedIn. We're gonna publish it in these days.
Okay. Thank you. And the next question, did you miss any functionality in Capella that would really help doing the reverse engineering work?
Computational capabilities, but I mean, probably the software is not supposed to do so. So, I mean, a coherent, all-in-one software for our purposes would have been better, but we were not looking at Capella for this. So,
Right. Okay, question from Laurent. What were the stakes of your study? Are there any expectation from any space agency or another entity?
so I'm not sure I understand the question. Maybe my colleagues.
So I can maybe rephrase it. So by stakes, I think Laurent means, why did you do that? What was the goal? And then did you do it in any relation with maybe the ESA or another entity? What are some expectations from a third party from your work?
Okay. Thank you very much. No, basically it was work on our own as part of our university course on system engineering and operations. So in collaboration with of course, our supervisor, the Professor Lavagna of this course, but not with any agency or external entity.
Okay, next question. Did you connect your Capella model to any PLM system for reuse of configuration control and manufacturing of parts for future mission?
No, we didn't use any PLM systems, and we just, let's say, used the main Capella features in order to understand the basics of system engineering, as the course we attended was an introduction to system engineering. So we just stayed with the, let's say, basic features of the software.
Well, that's all we have in the chat. So I'm gonna close the event for today. Thank you very much, guys. I'm gonna bring you off stage.